Hello and welcome to this lecture on fundamental of electric drives. In the last lecture, we were discussing about the load equalization by connecting a flywheel. We will continue from that lecture. Now, in this case, we have connected a flywheel here to the motor and load combination. This is the flywheel, and the load torque changes in a rectangular fashion. It is a pulsating load torque, which is here, and what we want here, that the motor torque should change between a minimum value and maximum value, between T minimum and T maximum. So, we have been given with the motor characteristic. The motor has a speed torque characteristic. The motor speed torque characteristic is given to us. So, the speed torque characteristic of the motor is a straight line. It is given to us as a straight line here, and the equation of this straight line is omega m is equal to omega m naught minus small k into T, where T is the torque. So, omega m is equal to omega m naught minus k T. This is the characteristic of the motor, and the load is pulsating in nature. So, we have to use this motor characteristic to decide about the inertia of the flywheel. Now, let us just write down the dynamical equation. So, we have the motor characteristic, which is omega m equal to omega m naught minus k T. So, we find out the derivative of this, omega m by dt, d omega m by dt. Now, omega m naught is the no load speed. This is the no load speed. This is the speed when the load is 0. Okay. Now, this is constant quantity. So, this derivative will be equal to 0. So, what we get here is minus k is a constant here, dt by dt, and we will be applying our equation. The equation is j d omega m by dt, the motor equation, plus T L equal to T. So, this equation is the popular, very popular equation for the load and motor, d j d omega m by dt, which is the inertial torque, plus T L is the load torque, that is equal to T is the motor torque. Now, what we do here is we substitute for d omega m by dt from the previous equation. So, from this equation, let us say this is equation number 1, this is 2, and we get equation number 3. So, we substitute for d omega m by dt from equation 2. So, what we get here is minus k j dt by dt plus T L equal to capital T, or we can write down in the following form, that k j dt by dt plus T is equal to T L. So, finally, we get this equation. So, this is the equation which is a first order differential equation in T. T is the motor torque. So, this is a first order differential equation. And we need to solve this equation. So, we have to solve this equation. Let us see how we solve this equation. So, we have this equation which is kj dt by dt plus capital T is equal to TL. So, this equation has to be solved. Now, if we solve this equation has got the following solution: T is equal to T initial plus T final minus T initial into 1 minus exponential minus T by tau m. So, we have a time constant involved here. Now, in the equation which we write here, we have the time constant tau m is equal to k into j. K into j is the time constant here. So, the solution of this equation is T equal to T initial plus T final minus T initial into 1 minus exponential minus T by tau m. So, we have to find out what is T initial and what is T final. So, if we go back to our pulsating torque that we have drawn previously, we can draw it once again. So, this is the pulsating load torque, which has got a high value and low value. So, this has the high value TLH and this is the low value TLL, and what we want here, the motor behavior should be like this. So, this is the motor behavior T and this is the behavior of the load, which is TL. Now, we want that the motor torque should be confined between a T minimum here and here we have the T maximum and this is T minimum and T maximum. So, which means although the load variation is quite drastic, the motor torque variation is more or less smoothened out. So, it is between something like T minimum and T maximum, and this curve is an exponential curve, T minimum to T maximum to T minimum. Now, this time for which the torque is high, we call this to be TH, and the time for which the torque is low, we call this to be TL. This equation k j dt by dt plus T equal to TL is applicable to the motor behavior, which is varying between T minimum and T maximum, and the T initial, let us say for time between 0 to TL. So, this is our origin. So, for this region we can write down what is T initial and T final. So, what is T initial? So, if we see this particular curve, T initial is T minimum, the minimum value of torque. So, T initial is T minimum. What is T final? T final here, if it is allowed to continue and if we maintain this high load torque, T final will ultimately reach TLH. So, T final is TLH. So, we can substitute these values in the previous equation, and for this zone we can write the equation T is equal to T minimum plus TLH minus initial is again T minimum here into 1 minus exponential minus T by tau m. Now, from this equation we can find out what is T maximum. This equation is applicable for T between 0 to TL. So, for this zone we have this equation at T equal to TL, at T equal to TH here, this is TH, we get T is equal to T maximum. So, when the time reaches T h, the torque actually reaches T maximum. So, in this case we can write here T maximum is equal to T minimum plus T L h minus T minimum into 1 minus exponential minus T h by tau m. Now, this is the equation from which we can find out what is the inertia. Now, from this equation we can readjust the various terms here. T maximum minus T minimum is equal to T L h minus T minimum into 1 minus exponential minus T h by tau m, or 1 minus exponential minus T h by tau m is equal to T max minus T minimum by T L h minus T minimum. Or finally, from this, after solving this equation, we can find out the value of tau m. So, tau m will be T h divided by natural log of T L h minus T minimum divided by T L h minus T maximum. So, this is the value of the time constant, which is T m, and we know that the value of time constant is k j. So, that is equal to k j here, or we can say that j is equal to, from this we can find out what is the value of j. So, j is equal to T h by k divided by ln T L h minus T minimum divided by T L h minus T maximum. So, this is the way to find out the inertia. Now, this inertia is a combined inertia, because we know that we have a motor here, we have the load in this case, this is the motor and we have the load, and what we have here is a flywheel. So, the combined inertia here is the j. J is the combined inertia of the motor, load and the flywheel. So, we can say that j is equal to j m plus j flywheel. So, when we know this j totally and we have the knowledge of the motor inertia, motor and the load inertia, we can find out the inertia of the flywheel. So, the inertia of the flywheel is equal to the combined inertia minus the inertia of the motor. So, the combined inertia that we find out is T h by k divided by natural log of T L h minus T minimum by T L h minus T maximum. This is j minus j. So, this is the inertia of the flywheel, so that the actual torque of the motor can vary between a T minimum and T maximum. So, this is called the load equalization, in which we can connect a flywheel to almost equalize the load torque between T minimum and T maximum. So, now we will just do an overview of the DC motor characteristic. We have already studied about DC motor, but we will be doing an overview of the characteristic of DC motor. Now, first of all we take a shunt motor. In a shunt motor, what we have here, we have the armature and we have the armature, some resistance is placed here and we have the field. We have the field resistance. So, this is the armature and we have the field in this case and the armature resistance and the field resistance. So, the resistance of the armature is R and resistance of the field circuit is RF. And what we do here, we apply a DC supply in this case to both armature and the field. So, we apply a DC supply and the motor draws a current, that is I. Part of this current flows to the armature and part of this current flows to the field. So, what is R here? R is the total resistance of armature circuit. What is RF? RF is the total resistance of the field circuit. So, we can write down some equation. First of all, I is equal to the current which is drawn from the power supply, the DC power supply is equal to the armature current plus the field current, I equal to IA plus IF. Now, in the armature circuit equation, we can say here applied voltage V, the motor has a back EMF, that is E. We can say that we have the back EMF plus the drop in the resistance IA into R. And what is this back EMF? The back EMF is some constant into the flux into omega m. Omega m is the speed. And we have the third equation, which is the torque equation. Torque is given by K phi into omega m. So, these are the three equations of DC motor. The voltage equation, V is equal to E plus IA into R. The back EMF equation, E is equal to K phi into omega m. Then we also have a third equation, which is called the torque equation. The torque in a shunt DC motor, when we keep the flux almost constant, T is equal to K phi into omega m. Now, from this we have to find out the speed torque characteristic of a shunt DC motor. Now, we have this equation V is equal to E plus I into R, that we can write as E is equal to V minus IA into R. What is this back EMF? Back EMF is K phi into omega m, that is equal to V minus IA R, or omega m, the speed of the motor is v by k phi minus I a r by k phi. Let us substitute for I a. I a is torque by k phi. So, we finally get this equation T r by k phi square. So, we have kept the field constant. The field current is kept constant, we do not change the field current. So, we have a flux that is phi. So, this is the equation for speed. Now, the speed equation is v by k phi minus T r by k phi square. So, this is the equation of a straight line. We are here plotting omega m in the y axis and torque in the x axis. So, this is the applied voltage. The k phi is constant because we have assumed that the flux is constant. So, k phi are constant. So, if k phi is constant and t is variable, this is one variable and omega m is other variable. So, we have the variable t here and variable omega m. So, we are basically plotting omega m versus the torque. So, we are plotting here speed versus torque, and this is the first term which is called the no load speed omega m naught, and r by k phi square is something like the slope of the characteristic. So, we get a straight line here and this is the no load speed omega m naught, this is the no load speed, and the slope of this characteristic is r by k phi square. So, this is the characteristic of a shunt DC motor or same as a separately excited DC motor. Now, what we have to do here, we have to control the speed. How do we control the speed of a shunt DC motor or a separately excited DC motor? That we will be discussing here. Now, let us say speed control of a shunt or separately excited DC motor. So, let us first draw the characteristic omega m in the y axis, torque in the x axis. The characteristic is a straight line characteristic like this. This is the no load speed omega m naught. So, we have omega m equal to omega m naught minus something like k into t. This is the nature of the characteristic, or if we write down the exact value, omega m is v by k phi minus r into t by k phi square. Okay. The same k here and we have the same k here. Now, in this case, the first method of control is by armature resistance method, armature resistance control. Now, if you change the armature resistance, we are basically changing this R. Now, when we change R, the slope of the characteristic will change, but the no load speed will remain the same. So, the characteristic will change like this. So, when we go on changing the armature resistance, the characteristic will change like this. This is for R 1, R 2, R 3 and R 4. Here we are talking about armature resistance control. So, we are changing the armature resistance. Here the resistance values are R1 is less than R2, is less than R3, is less than R4. So, we are basically increasing the armature resistance. So, when we are increasing the resistance, naturally the torque speed characteristic will change, and if we have a load torque here, suppose this is our load torque which is almost constant, this is T L, the intersection of the motor and the load characteristic will decide the operating point. Now, here the originally we had one speed. Now, when the resistance was changed, the speed will change here, we have the second speed, then we again increase the resistance, the speed will change, we again increase the resistance, the speed will change. So, initially we have omega m1, then omega m2, omega m3 and omega m4. So, when we increase the armature resistance, the speed will change. So, this is how we do the speed control by armature resistance method. Okay. But this is not a very efficient method, because we know that if we introduce armature resistance, there will be I square R loss. So, this is one of the ways. Let us see, do we have some other ways of speed control. The second method of speed control is armature voltage control. Now, in armature voltage control, what we do, we change the armature voltage. Now, this is the torque speed characteristic, omega m versus the torque here, and this is for one value of the voltage. Now, we change the voltage here. So, we have got omega m equal to V by k phi minus T r by k phi whole square. Here what we do, we change the armature voltage, this variable is changed. Now, when we are changing V, the no load speed is changing. So, when we are changing V here, what changes is the no load speed, but the slope is not changed. This quantity, this is almost constant. The slope is constant, but the no load speed is changing here. So, when the no load speed is changing, we have the family of curves which we can plot like this, V1, V2, V3, V4. So, we are varying the voltage. So, this is armature voltage control. And in this case, V1 is greater than V2, is greater than V3, is greater than V4. And if we have load characteristic which is like this, we will have various speeds here. This is omega m1, this is omega m2, we have here omega m3, and then we have omega m4. So, when we are changing the voltage, we see that the speed also changes. Now, this is more efficient than armature resistance control, because there is not much I square R loss. We are changing the voltage amplitude. Now, the voltage amplitude can be changed provided we have a variable voltage power supply. If we have a DC power supply whose voltage can be changed, we can go for armature voltage control, which is more efficient than armature resistance control. So, we stop here for today's lecture. We will continue in the next lecture.